some more on waves in A-level physics, and we're going to have a look at some stationary waves. We're going to look at stationary waves in a string and stationary waves in an air column. So let's go and have a look at what we're going to try and do. What I want is to produce a system whereby I've got a pulley with a weight on it just to hold it sort of taut. We've got a string, and this string is connected to a loudspeaker, and this loudspeaker is in turn connected to a wave generator. So this is going to change the frequency of the wave, so we can wind that up, and we're going to have here a wavelength here, which is the point on the pulley to the point here, which is for our particular wave. And we're going to change the frequency of the wave, and when we change the frequency of the wave, what we're going to get is we're going to get the wave looking like this sort of thing, or maybe looking like this sort of thing. And they should be the same length, it's just I'm not able to draw that. And the distance here to there and back again, that would be regarded as one wavelength, and then this is going to be half the amount or twice the wavelength here. So we'll have a look. These are called harmonics. So let's have a look and see what we can do with these. And what I've got is a setup we'll go and have a look at. I've got my weight here on a piece of wool. I do have it normally on a piece of elastic, but this is slightly stretchy, and I've done this because it's thick and it's easier to see on the camera. When we try these things in real practical life, when I've got students gathering around, we can use a stroboscope to see some of this, but with the camera it's very hard to get the strobe working properly. So I've got here, can I have a camera operator for a minute? So here we've got the vibration generator, and that's going to go up and down like this. The string wool here is going to vibrate, and this is controlled by this signal generator here, which is going to put out the right number of hertz so we can get this working nicely. Now I'm just going to get down here so I can play around, and what we want to try and do is to try and get this to produce one complete wave. So let's see if we can do this. So at the moment it's vibrating, and I'm getting a node here. So I've got two, and I'm just going to try and lower this down. And I'm going to have to go down one more. Not quite. I've got to go over the top. about 6. It's a bit hard to see. It's around about there, is it? Are we getting sort of one wave going, sort of staying out? And as far as I can see, looking at the side of this, I'm getting this working. Now you're looking at the wrong angle here, so what we're going to do is we'll move the camera around a little bit so you're focused more on the middle. That's right, the wire's all caught. Move that out of the way. And we can just about see that working. It doesn't work very well at this low number, and this is about 6.8 hertz. So I've got this one about 6.8 hertz. Let's increase this up, and I've got to go over, and I'm going to take it to about 12. And round about 12 you can see that we've got 2 loops going. Try and see if I can get this a bit more accurate. I'm trying to get it as big as I can. Yeah, well, that's always a little problem we face here. That's caused by my extreme vibration ejecting the pin. Back there, about the best I reckon I can get, and that seems to be about 13.04. And it really doesn't like this speed, does it? It's ejecting the device. It's quite hard to put in. Right, let's move this up a bit. Now I've got it somewhat sort of awkward frequency, and it's not vibrating terribly well here. Let's see if we can get this better. There's 2. And I think now we've got nicely appearing 3. I might be able to adjust this a little bit more. Trying to get it as wide as I can. It's about there. So I've got 1 node, 2 nodes, and you're seeing this quite different on the screen than I'm actually seeing. that's about 19.26 hertz. If we try and go up to 4, I am really shaking this thing to death at the moment. At least you get it quiet for a moment in between. And judging by how difficult it is to get my banana plug in there, it is in there quite well. And now I've got 1, 2, 3 there. Go up a little bit more. And I've got IPC4. Let's adjust it a little bit better to make it bigger. About as big as I can get it there. So that's running at 25.73 hertz. So that's 4 nodes. And we'll take it up again. See if we can get this. Let's see what we've got. I've got 1, 2, 3, 4 nodes here, so I've got 1, 2, 3, 4, 5 waves, and that's at 32.37 hertz. Let's see if we can go for 6. It sort of still looks a bit odd in the camera, I'm afraid. Looks better in real life. Right, so let's take it up from 6 to 7. So I've got 1 wave, 2, 3, 4, 5, 6 there. I can see 6. I've got 5 nodes. And 32 we had before. I had 1, 2, 3, 4. Ah. Did I get that wrong? So here I've got 1 node, 2 nodes, 3, 4 nodes at this point. And then we'll go to 5 nodes. So here we've got our 1, 2, 3, 4, 5, and that's at 38.84. We'll do a few more. So let's go for 6 nodes. Is that about right? We'll see if we can tune it in a little bit better. Nodes 1, 2, 3, 4, 5, 6 nodes. And we've got our 7, 1, 2, 3, 4, 5, 6, 7 waves, and that's at 45.44 hertz. Let's see if we can go up another one and probably just about see one more. Got nodes 1, 2, 3, 4, 5, 6 here. That's back at the 45, so let's go up a fraction. Maybe here. I can see 1, 2, 3, 4, 5, 6, 7. And it's starting to become much smaller, and it's becoming much harder to see on the camera, although Paul's zoomed in a little bit. So that's 7 nodes, and that's at 51.95 hertz. And we'll try one more. I don't think we can probably manage more than this. These are becoming now really hard to see. 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes. And that's at 58.25. And we'll give you a rest from listening to that noise. Okay, so we've got some idea of this. Now let's also have a look at the length of this wave. And the length of this wave, it's going to be 1 meter and about 38 centimeters. So we're looking at this wavelength as 1.38 meters. So we've got our frequency and we've got our wavelength. Let's go and have a look. So looking at this table then, with this experiment, we've got here probably our fundamental at around about 6.8 hertz. Not very easy to measure. We should be looking at a doubling of each of these, but it's only about probably half due to having sort of wool as our main source. So 6.8 and then 13.04, then 19.26. So here we can see this one's 2 nodes, 3. There we are, we got our 1 node and 2. Right, so let's have a look. This here is the length of my wave here. So this is the wavelength of the wave, and I'm going to give that L. This here one here is going to be twice the wavelength, that's going to be 2L. This one here is going to be 2/3 of an L, and when we get to 4 waves here, we're on half an L, and we're looking at 25.73. It should be about 26, so we're not very far out. And then we can work out this one's going to be 2/5, isn't it? and then we can work out all of those others if we want to. So I'm just putting up what they are so you can see them. So going down, then we've got 4 nodes, 5 waves, and that's 32.37. 5, we've got 38.84. 6, 45. 7, we've got our 51.95, and 8, 58.25. So if I look at number of waves here, going from a half, this is then a quarter of the wavelength, and I can see that this one is 51, so let's call that 52. Half would be 26. The wavelength is, and that's fitting remarkably well within my experimental accuracy of the thing jumping out and of using wool and all the other bits and pieces. Okay, so let's see if we can take some more stuff from this experiment. So what we'll do is let's do a bit of work on this. Okay, so what do we know? Well, we know various bits and pieces. We know the wavelength here. The wavelength of the wave, it's a fixed wave, was about 1.38 meters in length. And what else do we know? Well, we know the fundamental frequency of this string, and that's around about 13 hertz. That gave us this basic shape from one end to the other, which is one full wavelength. So 1.38 meters, and that gave us 13 hertz. Now we can work out various things with this, and we've got a few formula that might be of help to us. Right, now what do we actually know that might help us here? Well, we know what the hertz are, we know what the frequency is, we know the wavelength. Well, what else do we know? Well, we know various formulas like V equals F lambda, so I've got a velocity, but this is not a moving wave, this is a stationary wave. So we've got various bits and pieces. We've got on this wave, not well drawn, this point here where it's not moving, this is our node, and where we're getting our maximum amplitude, this is our antinode. So this is a point of maximum movement, and here where we're getting minimal movement. So what can we do with this? Well, we can change various things. We could change the weight to see what happens if we change the mass. We can change the length of the string, and we can see what that does. So let's have a quick look before we get into any more and see what happens if we do this. Right, let's have a look at the system. We're going to put a little bit more weight on. And I'm going to put on, instead of what I had, which was 20 grams. I'm going to put on 100 grams of mass here. And we're going to see what difference that makes. So I've got some figures. Let's just go and have a look at certain ones. So I had this one at 52, so let's dial in 52, and we had about 51.95. Just because I want to get this accurate, it's not going to go very good. There we go, it's near enough. Let's see what happens. Around about this, I should have about 7 nodes, 8 antinodes. And what we've got is something completely different. I've got here 1, 2 nodes and 3. It looks remarkably different. By changing the tension in this string, the whole system now looks completely different. I'm going to see if I can hold it in place with a ruler. Right, so if I now take this down, let's see what we can do. This is my full wavelength, and we'll see if we can get it a bit bigger. About as big as I can get it, and we've got it now to get my wave struggling here a little bit. So I've got 1 node, 2 antinodes, and this is 32.91. If we go up to 3, so that's 2 antinodes, 2 nodes, 3 antinodes, that was about 52. Getting it to its maximum point. So 1 node, 2 nodes, and we can see this here. Paul zooms in a bit for me. We've got the maximum right here that I've got, and so that is at 49.44. And we'll do just 1 more. See if we can get now 3 nodes, 4 antinodes. Nothing happening if you don't get it anything like the right amount. Adjusting it to its maximum. 1, 2, 3 I've got there. I think I'm happy with that. It's about its maximum, and that's at 66.07.
Sorry, I don't know that one.
And we can see that we've got a very different set of values simply because I've used the same wavelength here. This again is 1.38, but the mass instead I've used equals 100 grams, which is going to make the string more taut, and changing that has completely changed all these values. What would happen then if we change the wavelength a little bit? Let's do that. So let's change the wavelength, and this time I'm going to set the wavelength to about 1 meter. Now I have a slight technical hitch here. And my slight technical hitch was the fact that my weight wasn't on the ground. So my weight's now on the ground, and we'll set this to 1 meter. Well, wavelength 1 meter. My weight isn't on the ground, and so let's see what we can achieve with this. Same frequency that we had a few waves on, and here we're getting something completely different. I have to hold it because it's moving along. And now we've got 2 and 2 is set at 46.09. So if we set the wavelength here to 1 meter with a mass of 100 grams, then this with 1 node, 2 antinodes is set to 46.09. And we'll just take it up and do one more. Too high there, go down a bit more. There we are, I've got my 1 antinode, 2 nodes, 3 antinodes. Its maximum there, 70.39, we're going to call it. So what we can see is that various things affect this experiment. We can see that changing the wavelength will obviously affect it. Changing the mass, surprisingly, affects the experiment quite a lot. And so if we're trying to sort of get things from this, investigating what's going on, then we have to take into effect all sorts of factors, since we can replace the mass, we can change in other words the tension on the wool in this case, we can change the material, and you can imagine that if we change the material, this is going to affect it quite a lot. Alright, now I want to have a look at another experiment, and this other experiment, we'll just take our string out of the way and have a look at something else about playing around with this. Right, so if we move that out of the way, I will introduce you to this experiment. Now what I've got is I've got some tuning forks, and we're going to have to work harder on this, because if you need to be able to hear this, it's going to be a lot more difficult. So we're going to spend a little moment here just getting some things set up. Right, okay. Now what we've got is our microphone coming in, and you can see that this is quite one of these quite big fluffy things, and I've got here a wooden box. I'm just going to play you the tuning fork. Yeah, you can just about hear that. Let's try again. I can hit it with one of my little hammers. Can't hear it that well. Let's do the same thing, but this time it's going to go on a box. Better still, I can fix this into the box, and I can bang it again. This tuning fork makes a much better sound at a certain sort of frequency. Let's take that one. I've got a few other tuning forks. And the first thing I'm going to do with this tuning fork is I'm going to put the same tuning fork back on. It's the same length as the other one. It's going to make a sound. Okay. Now I'm going to put a little thing on it, and this little thing we're just going to put at a different length. Right. Let's see what happens now if I sound this tuning fork. So with the device on there, without.
You might notice a different note. Let's lower it. Let's see if that makes any difference.
Well, we get some difference, but it's not as easy as I'd like. So I'm just going to try a few different tuning forks. And I've got middle C here, and I've got top C here. Let's just hear the difference.
But let's go down the scale. That's B. Let's try A. Let's now try G. And then after G, we're going to try F. Not very good F. E. And D. Not very good. And C. Some of those tuning forks sounded better than others. And what we should find is that A sounds about the best. So this is at 426 Hertz. Although this firm thinks that A is at a different hertz. That is what it's tuned for. And this sounds best at 440 Hertz.
Because this box is the right length to resonate at 440 Hertz. With this idea in mind, we're going to try a different experiment. So, what I've got is this setup. What we've got is a measuring cylinder full of water, and then I've got an open-ended tube, and I can move this up and down. Now we're going to get the sound mic in so we can try and hear this.
Not that good, is it? Let's change the length of this tube. Let's make it a bit shorter. Is that any better? Let's make it a bit shorter. Any better? Doesn't seem to be. So let's go a bit longer. So at the moment this is about 10 centimetres long. Let's make it 15 centimetres long. Not much better. Let's go up to a bit higher. This is now about 19. Ooh. Can you hear the difference? Paul's going to take the microphone and bring it pointing it down. You see it's got a bit louder.
Right, let's adjust this a little bit more. See if it makes it any better.
Now, is that louder than before?
I think it was a little bit. Let's take it up just a fraction more.
And what we're going to try and do is we're going to find that optimum bit where it's going to be
the loudest. So I'm going to release this and I'm going to do it quickly by ear.
About there.
I've got that measured at about 19 point about 2 or 3.
And that's about as
loud as I can get it. It's about that sort of loudness. So let's take stock of what we've got. I've got 440 hertz on here. It's labelled at 440 hertz. Whether Paul can zoom in or not, we'll wait and see. There we are, 440 hertz. Okay. And measuring this tube, then I'm about 19.4 we'll call it. So let's go and have a look. Now I've got my tube. Let's just draw this out. I've got my tube. It goes on a little bit more because it's inside another tube, and that's the level of the water, and we've measured that at 19.4 centimeters, and above that we're holding this tuning fork, which is at 440 hertz. 19.4 centimeters, that's no good to me. I need that in meters, so that's going to be about 0.194 meters. And I've got my hertz. I know that V equals the frequency times the wavelength. My frequency is 440 and this is 0.194 meters. Let's have a look at my calculator. Let's just try these out. So I've got 440. I haven't got 440. The mouse has got stuck. Right, here we go. 440 times 0.194, and that's going to give me about 85.36 meters per second. So I've got an idea about my velocity, but let's think about what we've got, because I've made a fundamental mistake. You see, the sound travels down here, hits the bottom of the water and comes up. So instead of this being this length of 19.4, in fact it's double that. So we're looking here at about double that distance. So we're going to be on 38.8 centimeters or 0.388 centimeters. I never trust my maths when I'm doing this online. But I think I'm right. Now let's multiply that distance then, which is double the distance, by my number, and let's take this and let's do the calculation. So we've got 440 times 0.388, and that's going to give me about 170.72 meters per second as my speed of sound. Way out. But then it's a very rough and ready experiment for trying to determine the length of a wave. What we can do better is to try a whole series now of different tuning fork frequencies, and we can try different lengths of air column, and we can see what we've got here. What we should get is some idea of what's going on. Now if I look at this particular wave, we've got this going down here and it's coming up. Well, I got that right, but this suddenly tells me that this wasn't the full wave. In fact, this is only a quarter of the wavelength. So my calculations were all wrong, because now it's 440 and we need to multiply that by 0.194 times 4 to give me the wavelength, and that 0.776 times 440 gives me a much more reasonable accuracy of now about 341.44 meters per second. So my reckoning with this simple experiment is that I've now got the speed of sound at around about 341.44 meters per second, and that's with my grotty hearing. And this way we've managed to work out the speed of sound in air, and all we had to do was understand some of the properties of waves a little bit better to work out that this was a quarter of the wavelength. So we went from understanding our length 19.4 centimeters, that would be double that for half a wavelength, and we can work out the speed of sound from that. So a couple of experiments there to give you some idea. One, to stimulate your brain to have a little think about how tension can affect a wire, can affect the sound. Something you probably know, that on a guitar, violin, cello, anything like that, if you tighten the string, the note changes. So we weren't really surprised about the tension and the note. If you look at a guitar, you look at a violin, the cello, they have different thicknesses of strings, and that can also affect the note. So there's quite a lot here about waves and stationary waves, that all to do with music and how it works. Next time we'll have a look at a bit more about waves, so I'll see you then. Take care, stay safe, and if it was useful, you can always subscribe. Thanks for watching. Bye bye.